DC-DC converter is the DC equivalent of an AC transformer. The buck converter is a DC-DC circuit, where the average output DC voltage is less than the input DC voltage. In the buck converter circuit, the transistor acts as a controlled switch and the diode as an uncontrolled switch, hence the buck converter step-down DC voltage. In this tutorial, you are going to learn how to design a DC-DC buck converter. Before we begin the tutorial, if you're interested in engineering simulations, coding tutorials, and more, be sure to hit the subscribe button and turn on notifications. Also, feel free to drop any questions or thoughts in the comments below. I'm always excited to hear from you. Now let's begin. When you open your MATLAB software, you should see this window. At the top of the home menu bar, click on Simulink. Now the Simulink window is opened. Click on the blank model template. This window opened is where we will be designing our model. Now click on the library browser icon to select the building blocks of our circuit. With the Simulink library browser opened, scroll down on the first panel to Simscape. Click on the Simscape drop-down arrow. Click on the Power System drop-down arrow. Click on Specialized Technology drop-down arrow. Click on Fundamental Blocks and add the Power GUI component to the model by right-clicking on the component and selecting Add Block to Model Untitled. Click on the Fundamental Block drop-down arrow. Click on Electrical Sources, add the DC voltage source to the model. Click on Elements, scroll down on the second panel and add Series RLC branch to the model. Click on Measurement, add the current measurement and the voltage measurement components to the model. Click on Power Electronics, add the diode component and the MOSFET component to the model. Scroll the first panel up, and click on Sources. Add the pulse generator to the model. Click on Signal Routing, add the Go-To component to the model. Click on Commonly Used Blocks, add the Scope component to the model. Close the Simulink library. Separate all the components. Double-click on the DC voltage source to show its properties, and change the amplitude to 230. Click Apply and OK to apply the changes. Open the MOSFET properties, scroll down and untick the Show Measurement port, click on Apply and OK to close. Connect the positive port of the current measurement component to the positive port of the DC voltage source, and connect the negative of the current measurement to the MOSFET drain port. Rotate the diode as shown on the screen using Ctrl-R. Open the diode properties. For the snubber resistance and the snubber capacitance, type INF, then apply the changes. Connect the diode cathode port to the MOSFET source port and the diode anode port to the negative port of the DC voltage source. Open the properties of the series RLC branch, and select the branch type as L. Set the inductance value to 237E6 and apply the changes. Connect one port of the inductor to the junction where the MOSFET source port and diode cathode port meet. Duplicate the inductor component and rotate the duplicated component. Open the properties of the duplicated inductor and change the branch type to C, then change the capacitance value to 100E6 and apply the changes. Connect one port of the capacitor to the inductor, and the other port of the capacitor to the junction where the diode anode port and DC voltage source meet. Duplicate the capacitor and open the properties of the duplicated component. Select the branch type to R, and apply changes. Connect the resistor to the capacitor as shown on the screen. Duplicate the current measurement component. Connect the positive port to the junction where inductor and capacitor meet and connect the negative port to the resistor. Connect the voltage measurement to the resistor. Duplicate the voltage measurement component and connect it to the DC voltage source. Open the properties of the pulse generator, set the period to 1/10,000th, and set the pulse width, which is the duty cycle, to 70. Apply the changes. Connect the pulse generator to the gate of the MOSFET. Connect the go-to block to the current measurement and the voltage measurement blocks, and open the properties to label them appropriately. Right-click on the scope, select Signal and Ports. From the dialog box, click on Number of Input Ports, and set the number to 4, then click OK. Open the scope, select the View menu, select Layout and choose an appropriate layout for the result display. From each go-to block, drag the blue arrow at the end of the block to produce a From block, and connect the form blocks to the scope. Change the time to 0.5. Open the scope and click on the green Run button to start the simulation. Select the View menu and go to Style. Make changes to the colors of the display as you see fit. Apply each changes after changing the colors of each display. Double-click on the line connecting the From block to the scope, and type the name you want to see on each display. Open the scope and rerun the simulation. From the result, the source voltage is 230 volts, the source current is 160 amps, and the load voltage and load current are 150 volts and 150 amps respectively. If we change the pulse width of the pulse generator to 50, then rerun the simulation. The voltage source remains the same, but the source current, load voltage and current now output 50% of the source voltage. This is to show that the pulse width, which is the duty cycle, controls the output of the buck converter. It determines how many percentage of the voltage source will be seen at the load. Again, change the pulse width of the pulse generator to 25. Rerun the simulation. From the waveform shown, the load voltage and current only output 25% of the input voltage source. Thanks for watching. If you found this tutorial helpful, don't forget to like this video, share it with others who might benefit, and subscribe to the channel for more content like this. I'd love your feedback or any questions you have in the comments. Let's keep the conversation going. See you in the next video.